Hello, this is part 4 on our section about piecewise functions for empirical modeling. In our last video, we talked about a linear spline as a way of connecting multiple data points, and that worked well except for it leaves sharp corners anytime there's a change from function to function. And sometimes, some contexts, that won't really make sense, and so we'd like to find a way of doing something similar to a linear spline, but have nice smooth corners as opposed to the sharp ones. So how might we do that? Well, one thought is maybe a quadratic spline, because if I had curves here, maybe I would have a smooth, or what we'll call differentiable transition, and a quadratic would be the next easiest thing compared to a linear spline. So let's give that a try. So I'm going to define a generic quadratic function to be of this form. It's f sub I of x equals aix squared plus bix plus ci, where I ranges from, in this case, 1 to 3. So I'll focus on an example with 4 data points, but this will be true regardless. And then what will we do? Well, I basically need to solve for 9 unknowns. Because you'll notice each quadratic is going to have 3 unknowns, and because there's 4 points, that means 3 quadratics, so 9 unknowns total. So that means I need 9 equations. And each equation is going to correspond to some piece of information that I can glean from my situation. So just to give an example, f1 of 0 should equal 0, because that is referring to, if we draw a picture here, let's say we have some sort of curve here. These may or may not be quadratics in reality, but we need something to work with. So this is f1, this is f2, and this is f3. So that means f1 of 0 should go through 0, and f1 of 2 should equal 4. Likewise, f2 is going to go through these points. So f2 of 2 is also equal to 4, and then f2 of 6 should equal 1. And then last but not least, we have f3 of 6 is equal to 1, and f3 of 9 is equal to 5. So that's 6 equations. I need 3 more. And we can ask ourselves, well, what else do we know about our situation? Well, one thing that's different about this quadratic spline versus our linear spline is that we want a smooth transition at these points. In other words, we want the derivative from the left to equal the derivative from the right. And the way we can write that in equation form is to say that the derivative of f1 at 2 should equal the derivative of f2 at 2. And likewise, the derivative of f2 at 6 should equal the derivative of f3 at 6. And so what we have here then is we have 8 equations. So we need 1 more. And that's a problem because we really don't have any other information. The other problem is that one equation is an unsymmetric situation. We'll see what I mean more carefully here in a minute, but the problem is because of the symmetry of a scenario like what we have here, having one equation that we're off by, there's no obvious way of rectifying that without losing the symmetry of what we have. So quadratic spline almost worked, but we don't have an obvious way of fixing this dilemma, so we have to try something else. So the question is, what do we do now? Because we are short an equation, and in problem solving, we don't give up. We use some perseverance. We try to be creative. And one scenario we might think about is, well, just because it didn't work for this polynomial doesn't mean another polynomial might not work. So what if we went up a degree? And so what that means is, what if we consider a cubic spline? And so a cubic spline is going to be similar to what we just I've been talking about. It's going to be a function of the form aix cubed plus bix squared plus cix plus d sub I. And that's going to be true for every function that we need. It's still going to be n-1 functions. And so in this case, 3. Because each cubic now has 4 unknowns, we need 12 equations to solve for 12 unknowns. Now you might be thinking to yourself, well, this is worse, not better, because before we needed 9 equations and we could only find 8. So how are we going to get even more equations than before? Well, the advantage is that now that we have cubics, we can actually be a little bit pickier on what we require. And so we're going to require what we'll just call extra smooth transitions at the junctions. So in other words, we want the first and second derivatives to agree. So what does that mean? It means that our first 6 equations are still true, right? In fact, our first 8 equations still hold. Okay, so those haven't gone anywhere. All right, so I'm not going to rewrite those, but we'll just say the first 8 equations still hold. And because we want the second derivatives to agree, then we can add the fact that the second derivative of f1 at 2 should equal the second derivative of f2 at 2. So that's basically just saying that this point right here, a cubic, is going to have both the first and second derivatives agree. And hopefully we have enough flexibility in the equations to do that. And likewise at the other data point, the second derivative of f2 at 6 should equal the second derivative of f3 at 6. So we need 2 more equations. Now, it might be tempting to say, oh, well, I'll just have the third derivatives agree. But unfortunately, that's not going to work. So, because we've exhausted what we can do with these interior points. If you think about it, not only do we have the functions going through all these points, but we've required a lot of these 2 interior points that both the first and second derivatives agree. And so if we try to require the third derivative, well, if you think about cubics, the third derivative would be reducing our function so much that there wouldn't be anything left really to work with. But we haven't done much with the endpoints. And so that's the key to solving the cubic spline that we didn't have available to us before. When we only had 1 unknown, we could only work with 1 endpoint, which wouldn't make sense. But because we have 2 endpoints, regardless of how many data points we have, we'll always have 2 endpoints, and we'll always have 2 equations left. And so we actually have 2 choices. We have a clamp spline and a natural spline. And the key here is it just depends on what you know about your data. The clamp spline is nice if you know something about the trajectory of the data coming and going into the domain that we have. So what I mean by that is that we can say something like the first derivative at the first point, in this case 0, would be some constant, I'll just call it k1. And the first derivative at the last endpoint, so that would be f3 prime at 9, would be some constant, I'll just call that k2. So these are slopes. So if for some reason we knew the slope here at 0, 0 is 1, then k1 would be 1. If we believe it's horizontal, then k1 would be 0, and so forth. So it just depends on what we know about the data, if anything. The other option is to assume the second derivative at the endpoint is 0 for both of them. So this is what's known as a natural spline. It's basically saying, well, I don't know anything about the slope, so I'm just going to assume that the derivative of that derivative is basically 0, and then go from there. So if you don't know anything about what K1 and K2 should be, I encourage you to put zeros in, and notice in either case, we have 12 equations. And this is what we needed to solve our problem. We'll look at an actual example in the next video. We'll see you there.